Okay, hey folks, recording this last and final video for our chapter 6 on thermodynamics. So I'm going to go through these last three learning goals. So know Hess's law and how to balance multi-step reactions. Okay, we're going to do that. Be able to calculate enthalpy of formation and enthalpy of reaction. There's a formula that goes along with this. This will be pretty straightforward. And then know how to calculate fuel values given the enthalpy of combustion. Okay, so we're going to wrap it all up. So to start, Hess's law. So in Hess's law, I don't have like a formal definition of Hess's law here, but basically what Hess's law is saying is in chemistry, there are often multiple steps in a reaction. So up to now, we've only ever showed you one step, which would be the observed reaction, or sometimes I call that the global reaction, the main reaction. In chemistry, there's almost always what we call a mechanism. So in other words, chemistry occurs in steps. Okay, so for this simple reaction between nitrogen and oxygen to make two NO2 to make two nitrogen dioxides, it actually starts with step one, where one single nitrogen reacts with one single oxygen and makes two nitrogen monoxides. And we note that that's an endothermic step, that first step being positive 180 kilojoules. So now in the second step, check this out. The product from this first reaction now becomes a reactant in the second step. And it reacts with another oxygen to make two more nitrogen dioxides. And this is an exothermic step. Okay? And so what's important to note, when I add step one and step two, check out what happens. So the two NOs cancel with the two NOs, right? So later on in Chem 110, we'll start to call this an intermediate. So we're not going to talk about intermediates too much in this class, but it is a chemical intermediate. It appears in one step and disappears in another step. Okay. We also note that, look, there's two oxygens that get added up to give me my two oxygens right there. All right. And everything else follows down the line as we're adding these reactions together. And what we get is the main reaction. Okay. And also what's important to note in this is Hess's law here. When I add these two steps together, I also add the enthalpies together. Okay? So positive 180 plus negative 112 gives me 68 kilojoules. So overall, globally, this reaction is endothermic. Okay? So graphically, we can see that right here on this chart. So here I have my initial state of nitrogen and two oxygens. Okay, there's this large endothermic enthalpy, 180 kilojoules, that's required for the first step. We often refer to that as an activation energy when a reaction has a large and positive first step. That's the energy that's required to activate the reaction, to get it going. Okay, and then so now we have the products of the first reaction, so the intermediates, right? And then those go on to react and release some energy. And so now my final state is right here. Okay, and so we have to remember, because enthalpy is a state function, only the initial and final state matter, which is shown right here, right? The initial to final. It's as if this mechanism is not even present. And that's why up to now, we haven't really been dealing or seeing with these mechanisms or steps, because they often can happen really fast. It can often be very difficult to get our hands on those intermediates and see what's going on. So we're usually only sensitive to the initial and final state in a chemical reaction, which is why we deal with this delta H as a state function. Okay. So now this is a bit of an esoteric exercise, but all the same, it's a good exercise for applying Hess's law. Okay. So suppose we want to calculate the delta H for this reaction right here below. Okay. But we don't know what any of its steps are. But we are given these, what I'm going to call elementary steps right here. So maybe we're able to look those up in a book somewhere. And we notice that they're not quite in the order or in the stoichiometric proportions that we need. So in this exercise, I'm going to show you how we can flip things and rearrange them to add these two steps together to give us this global or observed reaction. Okay? So, this is kind of like solving a puzzle, and everyone's going to do it a little differently, so I'll just walk you through how I do it. So the first thing I notice is that ammonia is a product right here in this reaction. However, it is a reactant in this reaction. So the first thing that I want to do is take this step number 1 and flip it. Okay? So I'm going to write it as the following. I'm going to write it as 3 halves H2. I'm going to skip writing the phases for now just to make life a little bit easier. And so I'm just writing this above reaction in reverse. Okay? And when I do that, it changes the sign of delta H. So up here it was positive 46 kilojoules, but when I flip it, it becomes negative 46 kilojoules. Okay? So now the next thing I recognize is that I also have this reaction here where H2O is a product, but down here I need it to be a reactant. So I'm also going to flip this reaction. Okay, so I'm going to write that as 2H2O goes to 2H2 gas plus O2 gas. And of course, because I flipped it, I also changed the sign again. So positive 484 kilojoules. Okay, so now this is the first step that I like to do. I like to get everything kind of arranged in the right order. But now what I'm going to have to do is multiply these reactants just like we did with balancing redox reactions to get the right number of reactants. Okay. So the first thing I notice is I need 4 of these ammonias, and actually what I'm realizing is I think that, let's see, I'm looking at my cheater notes, and I think that I have a typo in this problem. Okay, let me check really quick. Oh my God, yes, I have a typo in this problem. Okay, so there should be a 2 right there. Okay, there should be a 2 right there. I'm looking at my cheater notes right here. Whoops. Okay, so what that means now, what I want to do, to get 4 ammonias, I'm going to multiply this whole thing by 4. Okay, times 4. And so not only is that going to give me the right nitrogen and ammonia, right? 4 times 1/2 gives me 2 nitrogens and 4 ammonias. But I also need to remember that I'm going to multiply this by 4 as well. Okay? And so now, let's see. So when I kind of scan through, right, I can see 4 times 1/2 nitrogen is going to give me 2 nitrogen, which I need. And 4 times NH3 gives me the 4 ammonia. So I also need that as well. Okay? And so that's also going to give me a whole bunch of hydrogens, which hopefully I can cancel. All right? And so now I'm going to need to do the same on this reaction. And what I'm going to do, I'm going to scan through and see, so for example, I've got 3 oxygens right here, but I've got none. So I'm just going to say times 3. And yes, that's going to be perfect because, right, I need 6 waters and then the 3 times 2 is going to give me my 6 waters. And we'll see what happens to the hydrogen. Hopefully that cancels out this intermediate hydrogen, okay? And then I also remember that I'm going to have to multiply this energy by 3, okay? So let's keep that going. And then now I'm going to add them all up, okay? So I've got 4 times 3/2 hydrogen. That's going to give me 6 H2s plus 2 N2s. And now 3 times 2 gives me 6 H2Os. And then look, now I've got 6 H2s plus 3 O2 plus 4 NH3. And I can see my hydrogens cancel. Okay, so great. So now I've got 2 nitrogen plus 6 oxygen plus 3, plus 6 H2O plus 3 oxygen plus 4 ammonia. So that gives me the correct answer. And then now down here for my delta H, it's going to be 4 times negative 46 kilojoules plus 3 times 484 kilojoules. So let's see, that's going to give me 46 negative times 4 plus 3 times 484 equals, and let's see here, what do I get? Yes, wonderful, that's the right answer. So I get positive, let's see, because this is addition, it's going to go to the nearest whole joule. So that's 12, 1268, 1028, 1268 kilojoules. So endothermic, okay? So now I've got another problem here that I'm not going to work out in the interest of time, but you should definitely try and work out this problem for yourself. I am going to put the solution to this in the notes. So I'll work this one out and include it in the notes, okay? So I want to try to keep these videos shorter, so that's why I'm going to skip doing this. So this will be good practice for yourself. Okay, so moving on to the next section here. Standard enthalpies of formation and reaction. So I already kind of talked about these briefly at the very beginning, okay? We note that both of these are fairly similar. The delta H of reaction and the delta H of formation. Both describe the heat that accompanies a chemical reaction. This one, the delta H reaction, can be generic for any type of chemical reaction, okay? Just the change in enthalpy that accompanies the chemical reaction. This one, the enthalpy of formation, is very specific to the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard state. Okay, so that's very specific. This is the one, the delta H of reaction, that's what we're going to deal with mostly just because of it's generic. We can apply it to any chemical reaction we want, okay? And so this is how we calculate enthalpy of reaction. Just like we note in a state function here, it's always the final minus the initial. Our delta H of a reaction is always going to be, right, the final state minus the initial state, which is products minus reactants, okay? So now I expanded this equation, and I know this looks scary, but it's not at all, okay? So let's walk through this. So that's saying the sum, right, for sigma, okay? This is saying the number of moles of product or the number of moles of reactant, and this is multiplied by the specific delta H of formation of an individual product. So yes, that's right. For delta H of reaction, we have to know the specific delta H of formation and note the standard, right? Meaning at 298. So standard at 298K, okay? So we have to be able to look these values up, okay? So one thing to note, oops, my my table was missing a header here, okay? One thing that's important to know, okay, so this is a rule that you've got to know. For all elements in their standard state, so all, we'll actually just say all things in their standard state, the enthalpy of formation is always 0 because they're already in their standard state, okay? So you notice here's just a few examples, such as aluminum metal, sodium metal, potassium metal, nitrogen gas, oxygen gas, chlorine gas, hydrogen gas. So because this is at 298 K, right, whatever we expect that substance to be at 298 K, that is its standard state. And so if it exists in that standard state in a chemical reaction, we can automatically put 0 for its enthalpy of formation, okay? As it turns out, if something is not in its standard state, we would have to look it up. And so what I want to show you here, I've got a table from the book. This is Appendix 4 from your book. Lots and lots of data, and I'm going to scroll down to table A4.3, thermodynamic properties at 25 degrees C, so that's the same as 298 K. So this is standard states. And then check it out. Not only is the molar mass listed, but look, there's that delta H of formation, okay? Don't worry about this S and this delta G. We'll talk about those in Chem 110. But now if you scan across this middle column here, these are the enthalpies of formation that we could look up for a calculation, okay? And so if we scan down this list, right, it's a huge, huge list of all of the possible enthalpies of formation we would need, okay? So that's going to come back in a few minutes when we do a sample calculation, okay? So we're going to compare these two reactions in the sample calculation. There's the thermite reaction, and of course, if we were in the lecture hall, we would be observing the thermite reaction happening live, which is really cool. Sorry, we can't do that. And then we're going to do the same calculation for the combustion of octane, okay? So now what I have, though, I have a YouTube video here of the thermite reaction, and we're going to watch this, and we're going to try our best to pretend we're seeing this live.
Oh, hi. I'd like to do a little demonstration for you. It's known as the thermite reaction. And the thermite reaction is a mixture of two solids, aluminum powder, and this is the stuff that aluminum cans are made out of. But aluminum cans have all kinds of dyes to go ahead and put a label on there and wax on the inside. And this is pure aluminum that's been ground up into the powder form. And this is iron oxide. Fe2O3 is the compound formula, and that's known as rust. And here in Oregon, we have quite a bit of rust. So I mixed up these two solids, and I put them inside this little porous cup. This porous cup is purchased at a nursery because nursery people put soil and little seedlings and samplings and things inside there, put it in the ground and let it grow. Well, I've got the solid inside here and a little 4th of July sparkler. And the 4th of July sparkler will throw some sparks down in the mix, give it the activation energy to go. This is an extremely exothermic reaction, so heat will be given off. Our products are going to be iron, solid, and some aluminum oxide. This temperature that we reach is going to be hot enough to melt the iron product that we go ahead and make. So let me get this started. I'm going to light a little Bunsen burner here and light the sparkler. So at the beginning, you'll know that it's just sparks.
I love that he uses a Bunsen burner to light a sparkler.
More than just the sparks.
So this is just the sparkler happening right here. Okay, there's the thermite reaction.
That's molten iron that's dripping out of the bottom there. That's liquid iron.
So I'm going to pause that for a minute. That is awesome. There is so much heat released in this reaction. It's so exothermic that it makes the iron go molten. It melts the iron, which is several thousand degrees, okay? So you can see from my balanced chemical equation, right? Iron's solid as a product, but remember, this is all about the initial state and the final state. So if we wait long enough, that iron will solidify. It will eventually cool down and solidify. However, during the mechanism, during the steps of this reaction, there is so much heat evolved it liquefies the iron.
The cat food can underneath it is just for effect because the iron just ripped right through that aluminum can and it's kind of on fire.
So there's a drop of liquid iron.
It's catching the iron so that it doesn't go into water or hit the table or something like that because it's at about 3250 centigrade. It's very, very, very
3,250 Celsius. Pretty cool. So we do that live in the lecture hall when we can, obviously when there's not a pandemic going on. So in any event, and there's lots of cool videos out there on the internet of the thermite reaction. The Mythbusters a while back like melted down an entire car with a thermite reaction. And also, little did you know, this is some of the starting mixture in the solid rocket booster on the space shuttle. Okay? So they actually use this to activate the solid rocket booster, which is really cool. And then it sends a ship up to space. So we're going to calculate these. So using this idea that delta H is H products minus H reactants. We're going to do this reaction. Okay? And so what we would need to do is look up the individual heats of formation for each one of these things, right, using this chart. Okay, I've already done that for you so that we don't have to, so I'm going to close my YouTube video here so that, there we go. So I've already looked these up for you, okay, so that doesn't take as much time. However, you should familiarize yourself with how to find these values, okay. So one, we note that aluminum, it's in its standard state at 298 K, so it has an enthalpy of formation of 0. Iron has an enthalpy of formation of 0. If I were to look up iron oxide, I would find that it's negative 824.2 kilojoules per mole. And if I were to look up the value for aluminum oxide, I would find that it's negative 1675.7 kilojoules per mole. Okay? And so now I'm just going to apply this formula right here to calculate the enthalpy of reaction. Okay, so I'm going to write that as delta H standard reaction equals. So now I've got to sum up all the products. Okay, so we've got the aluminum oxide here. Okay, so that's negative 1675.7 kilojoules per mole. Okay, and then let's see, now that's plus the iron, it's 0, so I know that, you know, plus 0 is not going to affect this, but I'm still going to write that so I can see that what I need to do, because there's 2 irons, I need to say 2, and even though that's 2 times 0, right, this is good practice for using that coefficient, okay? And so now this is all of my products. So I'm just going to write that down below. So this is technically the sum of all of my products, right? So now I'm going to subtract it by the sum of all of my reactants, okay? So now I've got the iron oxide, that's negative 824.2 kilojoules per mole, and there's only one of them, so I don't need to worry about that coefficient. And then plus for the sum, 2 aluminums, and then of course it's times 0, but we're just writing that there to be complete. Okay. And so now when I go through and do this math, and we have to remember to apply our negative signs, right? Don't forget to do that, right? Negative 1675 plus 2 times 0, and look, minus, that's going to make that a positive, okay? So the way that's going to go, right, that's, let's see here, clear that out, 1675.7 negative, and I'm going to say now that's minus 824.2 negative equals, and yes, that is the right answer. So negative 851.5, and this is just units of kilojoules, because look what happens. I didn't write this out here, but we recognize that there was technically times 1 mole of iron and times 1 mole of the aluminum oxide. So that's just negative 851.5 kilojoules for the heat released. So let's think about what this means. This is the heat released at room temperature, right? Final minus initial. We know that the temperature goes crazy high and makes the iron molten. But at the end of the day, after the reaction is done, and of course, if we were to use exactly 2 moles of aluminum and exactly 1 mole of iron oxide, right? If we were to use those amounts, that's how much energy would get released, okay? And we note the negative sign tells us it's exothermic, and definitely we saw this reaction was exothermic, okay? So let's do it for this reaction, okay? Let's do it for the octane. And I'm going to do it for octane balanced to just 1 mole of octane. So I meant to write that way instead. Okay, so to get the reaction to its simplest terms as far as the octane, because we know the heat of formation of oxygen is 0 because it's in standard state. Okay, and so once again I collected all these values for you. So the octane is negative 249.9 kilojoules per mole for its enthalpy of formation. Of course, the oxygen we know is 0. The carbon dioxide is negative 393.5 kilojoules per mole. And water as a gas, so when you go to look at that chart, you will see that water as a gas versus water as a liquid has a different value. So water as a gas, so steam, is negative 241.8 kilojoule per mole. Okay? And so now I can set up this reaction in the same way. I'm going to sum up the products and subtract them from the sum of the reactants. Okay? So now here, look, I've got 8 carbon dioxides, 8 moles of CO2 times 393.5 kilojoules per mole. So you can see there now how the mole and the mole unit's going to cancel. Okay? And now this is plus 9 mole of negative 241.8 kilojoule per mole. Okay, so that's the sum of my products minus the sum of my reactants. So that's just 1 mole of octane times a mole, so that's going to cancel the per mole unit. And then plus 12.5 oxygens, but times 0. So I did this one already, and I'm just going to write down the answer directly for you so you can see. But here we get negative 5,074 kilojoules. So look at this. That is more than 5 times the amount of heat released for the thermite reaction. That's crazy, right? If we were to combust 1 mole of liquid octane, which is actually quite a bit, we would get more than 5 times the amount of heat released. And the thermite reaction is classified as an extremely exothermic reaction. Well, look, folks, I mean, this is why we use octane to generate energy. As dirty as a source of energy this is, right, all of that CO2 it creates, as well as all of the byproducts that you get coming out of an automobile exhaust. There's a reason why we do it, because there's an enormous amount of energy released, okay? It's kind of one of the ironies of the world right now is that burning fossil fuels is actually very efficient. We get a ton of energy out of it, but it's ironic because it's also rather dirty. It creates a lot of pollution. So we have this kind of paradox right now, right, where we do recognize that burning fossil fuels is a very efficient source of energy, right? Those of you that have a gas stove know that you can heat up an iron pan with a gas stove really, really fast, okay? Much faster than an electric stove. It's far more efficient. However, it creates pollution. So that's one of the ironies of the universe right now, okay? And so that leads nicely into this discussion of fuel values and food values. I'm only going to talk about this very, very briefly, okay? So fuel value is, I kind of mentioned this earlier with the bomb calorimeter, okay? So fuel values and heat of combustion values are very similar. And so we'll say this delta H of combustion is the same thing as delta H of reaction, specifically for a combustion reaction, right? So we talked about how that delta H of reaction can be generic, right? We can use it for any type of reaction. So when we say specifically delta H of delta H combustion, it's the same as delta H of reaction, okay? So we just calculated that for octane, right? But now we note here that there are several other hydrocarbons that we have. Methane, so that's what you have in your stove, okay? And so let's see, oops, and kilojoules per gram, I just noticed that. Typo, kilojoules per gram. And so that's the kilojoules per gram of heat released, okay? So this is very straightforward to interconvert these two things. So for example, with methane, this negative 802.3 kilojoule per mole, okay, I can easily convert that into its fuel value by the following. So I just recognize that 1 mole of methane is, what is it? It's roughly 16.04. I've got that memorized. 16.04 grams of methane, okay? And so when and also for fuel value, you notice that it's all positive signs because in fuel value, we just report the positive value because we recognize that all combustion reactions are going to be exothermic, okay? So now if I just divide that by its molar mass, okay, yep, then I get 50.01. You can see that matches that nicely, kilojoules per gram. So these fuel values are much more useful because, again, we don't have a mole meter in lab. We have a mass balance, right? So you could weigh out how much gas that you're using in a reaction and very quickly get the total amount of kilojoules. So for example, suppose I burn 1 gram of methane. Well, if I burn 1 gram of methane, then I'm going to get 50.01 kilojoules of energy. Okay, so that's why the fuel value can be more useful for engineers, for example. And the very last thing I want to talk about, just very, very briefly, food values. Okay, so some of you already knew this, but in case you didn't, this is pretty interesting. So look at this on this can of soda, 140 calories per can. Well, check it out. A calorie is actually a unit of energy. And we have to keep track of this. So cal with a lowercase c is exactly 4.184 joules. And then I said, does this number look familiar here? Hopefully it does. So the heat capacity, the specific heat capacity of liquid water is 4.184 joule per gram per degree C, which is the basis of the unit calorie. And why is that? Well, because your body is mostly, oops, I wrote that backwards on this thing. Your body is mostly made up of water. So when you think about when you're consuming food for energy, where does all that energy go? An enormous chunk of it goes into just maintaining your body temperature, right? We did this calculation. Heat equals mass times CS times delta T. This is what your body is doing. It's maintaining some type of temperature, right? It's keeping your body warm. It's keeping your body much warmer than the surroundings, right? If you think about this system versus surroundings, if you're the system, you're about 39.5 or so degrees Celsius, I think 37.5 degrees Celsius, but the surroundings are like 25 degrees Celsius. So that's a huge temperature difference that your body has to maintain. which is why traditionally we give the unit of calories as the specific heat capacity of water, because your body is mostly water. Now, that being said, the calories that's reported on this can of Coke is actually a kilocalorie. So this is what I'll call a science calorie. So just 4.184 joules. A dietary calorie is actually a kilocalorie. Okay? I can't spell and talk at the same time. Yes, so that means one dietary calorie is actually equal to 1 kcal, which is 4,184 joules, or 4.184 kilojoules. Okay, so on this can of Coke where it says 140 calories, so that's 140 dietary calories, which is really going to be 140,000 regular calories. Okay, that's all that I'm going to say about the calorie and as a food value. Okay, so I think that puts a wrap on it, folks, for thermodynamics. So I know this is a lot, asking you to get through all of these videos this week. So thanks for doing that and getting caught up. I will see you during our live meetings this week.